everyone. Thank you for joining us today for our ALS Webinar Wednesday series. My name is Kelly Hall. I'm a marketing coordinator for ALS North America, and I will be facilitating the webinar today. Before we begin the presentation, I just have a few helpful notes. If you are having technical issues with our webinar platform or any questions, type your message or question in the chat pod, which is located at the bottom right. You can also select the hand icon to notify me of your status and I can assist you. All questions regarding the webinar material will be answered at the end of the presentation. Our presenters today are Pamela Heizar and Josh McKinney. Pamela Heizar is an experienced microscopist with nearly 30 years behind a variety of optical and electron microscopes. In addition to a Bachelor of Science from the University of Cincinnati, she has also completed numerous professional training courses. Currently, Pam is the Microscopy Technical Manager, presiding over the Microscopy and Asbestos Department of the ALS Laboratory in Cincinnati, Ohio, where she maintains the laboratory accreditations and certifications and continually seeks to expand the instrumentation, capabilities, and analytical offerings of the laboratory. Josh McKinney has served 19 years of experience in the environmental testing industry. Josh has worked in several different roles at the laboratory, including analyst, organics manager, project manager, and most recently, technical sales and business development for the ALS Environmental USA Laboratory Network since 2014. Josh also acts as the Columbus, Ohio Service Center Manager. Pam and Josh, thank you for taking your time to deliver this presentation today. I will go ahead and turn it over to you both.
Thank you very much, Kelly. Hello, everyone, and thank you for joining us today. I'm Josh McKinney, Technical Sales Representative for the ALS USA Environmental Network, based here in Cincinnati, Ohio. The bulk of the information we are presenting to you today is information on our analytical approach for detecting microplastics particles in water, of which the ALS Microscopy Manager, Pamela Heizar, will be the star of the show today. I'd like to go through with you briefly on an overview of microplastics and what they are, as well as the perceived environmental impacts. Microplastics are ubiquitous in the environment and have been detected in marine water, wastewater, freshwater, food, air and drinking water, both bottled and tap water. The physical definition from NOAA is these are small plastic pieces less than 5 millimeters long. And these come from a variety of sources. They're larger pieces of plastics that have degraded into smaller fragments. They're resin pellets used by plastics manufacturers, and also microbeads. These are small plastic beads that are used in health and beauty products, recently banned in 2015. These microplastics are tiny particles that pass through most filtration systems, ending up in our oceans and lakes, as well as potable water sources. Next, we'll talk about environmental impacts of the microplastics. So the microplastics do not easily break down into harmless molecules, as it's a long degradation process and they persist in the environment. There's a concern for accumulation of microplastics on beaches and in oceans. These microplastics are ingested by marine organisms, and that can cause their ongoing studies to see if there are adverse effects on the digestive tracts and reproductive problems for the animals. And these can be passed on to humans through consumption of seafood. There's also a concern and ongoing studies on adverse health effects towards humans, and concerns from the World Health Organization from a study and paper that they released in 2019. They are concerned with 3 areas, and that's particle size toxicity, chemical toxicity, and biofilms that can adhere to the microplastics particles. And those include free-living organisms, bacteria, and Legionella is an example. And now I'll turn it over to Pam with the laboratory analysis and approach from ALS Cincinnati.
Okay. Hi, everyone. I'm Pam Heiser. I am the microscopy and asbestos manager here at ALS in Cincinnati. And the first couple of slides we're going to go through here is some of the stuff that Josh has already covered, but I'll just explain a little more. So the plastic problem, everybody's aware there's too much, plastic garbage in our environment, but it's sort of compounded by a couple of facts. First of all, the exponential growth in the production of plastics, as you can see there in 1945, the U.S., these are all U.S. numbers, produced about 1 million tons of plastics, and then in 2014 that was 300 million, and already just a few years later there's another 100 million. So we're over 400 million tons of plastics every year. The other problem is that the hydrocarbon chains that make up plastics are inherently stable. They break down via photooxidation, but their form actually doesn't change much. So large plastic becomes small plastic, becomes microplastic, becomes nanoplastics, but they're all plastics and they all made up of the same thing. My slide just changed. Uh-oh. For no reason. Sorry. I'm going to get back to the right page there. No, forward. Sorry. Okay, there we go. So the final problem is that most of the things that biodegrade in our environment are eaten by microorganisms, which have been around for 300 or 400 million years. Well, plastics are synthetics and obviously have only been produced for the last 100 years or so. So those organisms haven't yet evolved to use them as a food source. So the fact that there's a huge rise in the number of plastics in the environment, that they don't break down very easily, and that the microorganisms that should be breaking them down don't know how to yet, is what is causing the massive numbers in our water system. Can I just get that? Yeah. Okay. So the standardization problem as far as testing is, because there's so many different sizes and so many different places that it can be, there's a number of questions you have to ask as far as, how you're going to standardize a test. Where are we looking? Are we going to look at just waters? Are we going to look at just drinking water or, seawater? Are we going to look at fish and mussels and whales, all the organisms that consume those things? Or are we going to look in people's, consumable foods like sea salt, and beer, and seafood, and other things that it's all been found in, microplastics and all those things. The other question is how to pre-treat things. Are you going to use manual separation? Are you going to use density separation or some sort of, pre-treatment to get rid of the things you're not looking for so that you can find the things you are looking for? And then there's the method of classification. Some people are just using visual classification in their testing. Some people are using micro FTIR, FTIR, Raman, and there's a variety of others. So there's so many methods out there. That, and each method might be better for a different thing, depending on what it is you're looking for, what you're looking in. So when Cincinnati set out to get a test, we decided the most important thing for us was for it to be, relatively cost effective and fast, because most of those methods require so many levels of testing that they become really kind of research projects and get really expensive. So we went with the SUNY study is what we call it. It's the State University of New York at Fredonia. Here's the reference to it. It's called Synthetic Polymer Contamination in Bottled Water. And this was, developed strictly for bottled waters. So in order to test anything else, we sort of had to adapt it. But basically, here's a study of their synopsis. They tested 259 individual bottles from, all kinds of different lots all over the world. So a total of 9 countries. And of everything tested, 93% of all the bottled waters tested contain some level of microplastic particles. 5% of those are greater than 100 microns, and about 95% of them fall in that microplastics definition category of 6.5 microns, or 6.5 to less than 100 microns. And on average, they found a total of 325 microplastic particles per liter. But the most important thing that came out of the study for us was that Nile red stain alone is sufficient for the rapid detection of polymerics in water. So it'll find, polyethylene, polypropylene, polystyrene, and nylon 6, but it can't tell the difference between them. So it just detects that they're there. They just glow. And I'll get into that in just a moment. So here's how we have applied it here. So we've done all the same sort of pre-work and injecting with the NR as done in the study, and use the same minimum incubation time. Then what we do, so we take this water and we inject it with Nile Red. We let it sit for 30 minutes in an ultrasonicator so that those particles will adsorb that Nile Red. Then that water is filtered through a 1 micron pore-sized glass fiber filter and examined under an optical microscope with blue crime light, which elicits fluorescence. So you're not looking at it with the naked eye now. Now you're looking at it through an orange filter under blue light, and all of those tiny little microplastic particles are fluorescent and glow. And I'll have some images for you in some upcoming slides so you'll see what I mean. But we collect images, and then we use a calibrated static image analysis to size and count those particles according to the ranges that we're interested in. So the results that you get are going to include all microplastics that are stained with the Nile Red, anywhere from 6.5 microns on up to 5 millimeters. And the reason for the 6.5 microns is because that's the smallest reliably detected particle at the magnification that you're collecting your images. So we can detect smaller particles, but we'd have to go up in magnification, which would reduce your analytical sensitivity, and it just kind of complicates things. So this is just a good jumping off point for somebody who's saying, I just want to know if there's microplastics in my water. So here's an image that shows you kind of what it looks like. So this is on the left, you'll see the stained particles are sort of that really bright, almost orangey white color. All of the other stuff is sort of background material. It could be sediment, it could be all kinds of other things. And so then what we do is we take our image analysis software and create a binary threshold image, which you'll see on the right. And it's only highlighting that certain temperature, if you will, of particle. And then the software is going to size that and categorize it according to its size. So there's a number of problems with this analysis, as you can imagine. So the number one problem is potable versus non-potable drinking waters. The SUNY study and ours it's developed just for drinking waters, which you can imagine are mostly clean most of the time. So it's really easy to see those microplastic particles once they're impregnated with that Nile Red stain. But we get lots of other waters that clients want to know if there's microplastics in, like groundwater or river water or wastewater, whatever. And there's so much other stuff in there that sometimes it's hard to see the microplastic particles. So there's two basic types of interferences. There's opaques and lipids. So opaques are any suspended solids like sediment and that kind of stuff that could be in any kind of water. And they might entirely cover up a microplastic particle or partially cover up a microplastic particle. And that kind of changes your results. It gives you a bias there, or it can, completely make it look like there's no microplastic particles there. Lipids are sort of the opposite problem. They are highly fluorescent in Nile Red. And so if you have a wastewater that has, let's say, a lot of like milk fat or some sort of fats or oils in it, that will become intensely fluorescent. And you'll think, oh my gosh, there's nothing but microplastics in here. When in fact, actually, there might not be any, but you're just getting a negative or a positive bias in that instance. And I'll show you some examples of what I mean here. So imagine this, where the eyeball is your eye looking through the microscope lens, and the black particles there are opaque particles that are sort of stacked on top of microplastics. You're not going to detect any microplastics in that, even though they're there. And that's the complete blocking of the microplastics. The partially is when there might be a little more spread out, and the lens and your eye are only going to detect those portions of the microplastic particles that are exposed from underneath the opaque particles. So here's a physical example of that. Here's on the top, the opaque particles in river water under ambient light. So you can see there's lots of sediment and algae and gross stuff in there. And then when we did it under the blue light, with an orange filter, you can see all of the fluorescing microplastics in there. And so it's going to detect all of that. But those big masses of black areas in the center, there's probably some particles underneath there that we're not going to be able to detect because they're being completely obliterated by the opaques. As far as lipids, here's that example again with you looking through the microscope and down. So the lipid particles that are emitting massive amounts of fluorescence are basically just going to wash out any microplastics and make it look as though the whole thing is plastic. Or if you can get them spread far enough, you might only see portions of the microplastics, but because the lipids are there too, it kind of makes them look larger. And so I'll show you an example of that. So here on the top, that's an example of a wastewater that we had that was so highly concentrated with lipids that the entire sample just glowed. And when we did the binary threshold of it, it would say there was this giant particle. And obviously that's the edge of the filter there, which I had to have for some sort of frame of reference for you to see what I'm talking about. So the way we resolve those interferences, this is where we modify the method a little bit, is simply actually through dispersing it. So we might take a highly lipid content material and take 1 or 2 milliliters of it, suspend that in 100 mils of, DI water, and then filter it and test it so that all those particles are spread out really far so that you can then detect the microplastics. So as you can see on the opaque particle one, there's an ambient light picture that shows all of those black particles kind of spread out further so that when we take the image of the microplastics, which is beneath it, you can then see the microplastics. And same with the lipids sample. It's still glowing, but the stuff that's really, really intensely bright is now the microplastics because the lipids have been spread out so far and wide. And so you're able to detect them. So that is basically the method that we use. Again, it's primarily developed for drinking and bottled waters and is highly reliable using Nile red stain to adsorb into microplastic particles and be able to count and categorize them according to size using static image analysis software. But we can also do other forms of water for people that we just have to modify the method a little bit. Also, the size parameters can be changed as well. Like I said before, we can find smaller particles. We just have to go up in higher magnification. You're looking at a smaller area, so your analytical sensitivity is going to be a little higher or a little lower, depending on what you're able to actually analyze. Things to know about this method, the limitations is that it doesn't distinguish between the different types of plastics because there's no FTIR involved or anything like that. It's simply, staining the plastics with this Nile red and then detecting them using the blue light. It also does no denoting of particle morphology. So we're not telling you how many fibers or fragments or microbeads or anything like that. It's simply categorizing them by their total area, their total area in microns. That's something that we can branch out to do, and we can even use some of the static image analysis data to determine how many fibers or fragments. So like if we're going to say that fibers are anything that has a length to width ratio of 3:1, we can add a calculation in there that will automatically do that and tell you. But so we're still working on some other adaptations of it. Apparently there's some other methods out there that that can help you determine which types of plastics are there based on the intenseness of the fluorescence, but we're not there yet. We're still working on that. And there's lots and lots of other microplastics methods out there. So the most important thing is for people to discern which method is best for them, which method is going to give them the results they want for what it is they're looking at. So if you have any questions, we're happy to take those now, or you feel free to email us later if you think of something. We're happy to answer those. Kelly, back to you.
Thanks, Pam and Josh. Yes, we will go ahead and open up the forum for questions now. Remember, you can write out your question in the chat pod section located at the bottom right of your screen. We will go ahead and give everyone a few moments to type in those questions. I did want to let everyone know that we do record our webinar presentation, and all participants of this webinar will receive a follow-up email once the recording is available to view. We post all of these webinars on our ALS Global website and our ALS YouTube channel in the webinar playlist. We did have one question already come in that during the presentation. Go ahead and put this through. Are there any studies which report actual adverse effects?
I haven't seen any yet. I know there's a lot of ongoing studies by a lot of different individuals and groups trying to determine, are there any adverse effects? And that's the number one reason that this testing hasn't actually been mandated for anybody, because as of yet, we don't know what the health effects are. Just like the PFAS that sort of got into our environment through all the nonstick pans. Now it's everywhere. Well, the same with microplastics. Now it's everywhere, and yet we don't know, is that affecting us physically or not? So there's a lot of ongoing studies, but I personally haven't yet seen anything that has anything definitive on what it would do to humans.
We have another question. This one is from Claire. Is there a way to treat the filter with a lipid-specific stain, which will not stain the plastics, in order to distinguish between them after imaging?
There is actually. This is my first foray into the whole, staining and fluorescence microscopy. So, but I'm aware that there's a whole slew of different kinds of stain that different materials either adsorb or reject. So you can either detect or eliminate certain things by using certain stains, but we haven't here in Cincinnati incorporated any of those yet. We're strictly just using the Nile red at this point.
We're still going to give it just a couple more minutes for any additional questions to come in. We had another question come in. Are you working on analytical methods for other sample media besides water?
I was. There's another study, I can't remember the name of it right now, but it was for sediments, for soils and sediments of the beach or whatever. And but the amount of equipment that was required just to pre-treat the sample, just to sieve out the different sizes of things and pick out fibers and microbeads and all that kind of stuff. The initial cash outlay on equipment alone was sort of cost prohibitive. So we haven't gone any further on that, because if we were to get all that equipment and do that test, the test itself would be so expensive. We doubt that we'd get much call for it.
So the number of potential actual billable samples on that project didn't justify the costs to set it up.
Right.
We had another question come in. Blair asks, has there been much demand for this test?
Josh can probably answer that, as how many questions he gets. As far as how many tests we've done so far since, making it available here, we've done hundreds. So
I would say I would relate it to like the PFAS timeline. So if this were on the timeline of PFAS, we're probably 2 years ago on PFAS. So we get very sporadic requests for it. There's not a huge demand, but I think the trajectory that it's on, there could be a potential large demand for it. I think a lot of it is going to be based on these ongoing studies and what it finds out on the human health effects. And like I said earlier, in 2019, the World Health Organization, they put out a paper, asking that more studies be done and more information be done. I would imagine we would be further along with, gaining that information if we were not in the situation we are in right now.
Interestingly, the number of tests that I've gotten so far, the majority of them have come from water suppliers, or even recently I got a big set from someone who was testing different water filter apparatus to see if they filter out the microplastics. And it was really interesting. We found that some of them are actually putting microplastics into your water. So there's a lot of stuff like that, instead of just individual homeowners or things like that. We're also working with River Water Keepers is an organization that is interested in how many microplastics are in the rivers around the world. So they're working on, but they're at a much larger scale. They're looking at larger particles than we are right now. And as far as I see the question about the cost of this test, currently the cost of the test is $250 for a normal 10-day turn. But obviously that cost will go down over time with the number of samples that we get in, helping to make up the cost for setting it up. And also it'll get faster and faster too. So I can perform the test a lot faster than the 2 weeks. It's just, that's a good timeline for ensuring that I'll be able to get it all done and get it right.
Yeah, we had another question come in too. As a newly joined PhD scholar, which area in nanoplastics you suggest to study?
I would suggest, what I'm most interested in and what I get the most calls about is the physical effects on humans. Most people just want to know, is it going to harm me or not? Because if it's not, I'll keep drinking my microplastic filled water. So they want to know, what is it doing to us? Is it hurting us? Is it responsible for anything? And so that's the area that I'm most interested in, is the physical effects on the human body.
I don't see any additional questions coming in at this time. Again, Pamela and Josh's information are here, as well as everyone on this recording, on this webinar today will receive the link to the recording as well as their contact information if you did want to contact them with additional questions about microplastics. So again, I want to thank everyone for attending today, and thank you to Pam and Josh for presenting. Hopefully everyone can enjoy the rest of their week, and we'll see you next Wednesday at our next Webinar Wednesday series. Thanks, guys.
Thank you.